This conference will now be recorded.
Hi, and welcome to Simulating Electron Beams Better with BOA, hosted by Calabasas Creek Research, or CCR. I'm Karen. I'll be moderator for today. This will be about a 45-minute webinar that will cover an introduction to CCR, an introduction to BOA software, and a demonstration of the BOA software. If you have questions, go ahead and drop those in the chat, or you can send them to everyone or to me in particular. And without further ado, I'm going to pass it on to Lawrence Ives, the president and founder of Calabasas Creek Research. All right, Lawrence, take it away.
Thanks, Karen. Calabasas Creek was founded in 1994 with the goal of developing the next generation of high-powered RF sources for scientific, medical, industrial, and defense applications. We recognized at the time that this would require 3D electron beam devices, and the current codes would not provide the capability we needed. So we teamed with Ansolve Corporation in 1998 to develop a 3D electron beam trajectory code using finite element analysis. Since that effort, we've received over $3 million of direct funding from the Department of Energy to improve and enhance the code. We've also contributed more than $1 million of our own hardware development programs to add features required to simulate those devices. In addition, we've added many new features requested by our customers, particularly from the X-ray industry, to meet their specific needs. We encourage our customers to suggest code improvements that will expand its capabilities and make it more useful for our users. BOA is a continually evolving design tool, and we're constantly improving and upgrading the code. We encourage users to submit requests for new features and capabilities. I'd now like to introduce Chuck Bowie, who is a primary developer of the code and the primary contact for customers and users.
Can you see my screen? Let me go. I'm Tuk Boy. Beam optics analyzer is a 3D particle tracker, tracking them under the influence of the electromagnetic fields. It uses the finite element method with adaptive meshing to solve for the electromagnetic fields and track particles in unstructured meshes and in a self-consistent manner. BOA is also a quasi-static peak code, tracking particle in time and solve for the electromagnetic field in every adaptive time step. BOA can also track the particle in the presence of harmonic fields. So the particle in BOA are able to generate some magnetic field when they travel in particle domain. They can also focus and confined by a magnetic field, which is either generated by a built-in magnetostatic field solver or imported from another package. BOA has a built-in measure with adaptivity and sophisticated GUI to import CAD models, input physical properties, and the boundary condition to perform simulation, post-processing, and displaying the source, the field, and the particles. It also has the optimizer to optimize the gun structure using a combination of SolidWorks, meshing, and nonlinear iterative algorithms. So BOA is capable to simulate multiple generation of secondaries using the Monte Carlo method with the Rutherford collisions and beta energy loss in solid. Using this technology, BOA can then generate the beta scatter field inside the solid, then simulate the temperature field with the built-in heat transfer solver. BOA can also optimize the surface current and power density to obtain the higher resolution surface field by a new novel shaded method without having to re-simulate or remesh. It is for X-ray simulation of thermal imaging due to electron impinging on the target. So this impinging electron generates a scatter field inside the target when they penetrate the solid. With this field and the heat transfer solver, BOA can then simulate the temperature of the target. BOA can also simulate the thermal stresses generated by the temperature field. So all these capabilities make BOA a truly multi-physics simulation software. So now I would like to introduce our principal scientist, Mike Reed, who's mainly responsible for research and development of electron guns and IF circuits. He will now to demonstrate how to import a models, get simulation done in BOA with actual working example. Mike, take over.
Okay. All right. Share. Okay. Okay. So what I'm going to do today is show you how BOA runs. I'm going to go through some examples to give you an idea of its capabilities and ease of use. I'll be doing 3 examples. One is a simple sheet beam, and this shows you the ability of BOA to do 3D modeling. And we'll go through the getting in the geometry, the model, setting the attributes of the parts of the model, adding an emitter and magnetic field, defining the mesh, and then running the simulation and displaying the results. And then we'll do, somewhat briefly, a generic X-ray tube. And this will illustrate how BOA can do a complex shape like a wire emitter. And then finally, a high resolution X-ray tube where we'll look at how you can refine the mesh to simulate a highly focused beam. To let you know, since I will be showing timings, I'm using a 12th generation i9 12900K processor. That's not quite state of the art anymore, but close. My machine has 128 gigabytes RAM, but BOA rarely uses any large fraction of that amount, and 64 gigabytes or even 32 is often more than adequate. Okay, so I've opened BOA, and basically the software, you just you can create a new project or open the project. I'm going to be running a project called BOA Demo that I've set up. And that shows, first off, the commands at the top there. And on the right shows the projects, the cases that I've already put in. And so we'll add a new case, which will actually be one that I've already started, but this shows what you do. You get to choose from a number of different analyses, whether it be just electrostatic or magnetostatic. Beam oxys is what we're going to do today. As Took mentioned, heat transfer, something that Took did not mention. What BOA can do is a static pick or a static field pick, but this models can be used for modeling bunched electron beams as long as the self-magnetic field is not important. And that's actually quite a very useful tool, for example, in IoTs and other types of microwave devices. We're going to do the electrostatic beam. And the next stage is to input the modeling. We generally recommend that the models be prepared with SolidWorks, but you can do it with other CAD packages. You generate an ACES file, and then that takes it. Okay, and then let's see. Well, there we go. Okay, and it just goes through the process of checking the model, and then it shows it's happy. Brings the model in. You can choose what parts of the model to use in the simulation. This is handy if your model is SolidWorks model is more complex and you have parts that simply aren't relevant. You choose the background. We're using a so-called infinite background, simulated by the boundary conditions of that type. You can use symmetry in a model, and then you get into the semi-infinite boundaries. Since this is a nice simple model, we'll do the whole thing. For this one, I'll show you the use of a fourfold symmetry in a moment. Okay, so that's good. And so then we're going to rotate the model around, and has a particularly nice interface. Allows you to manipulate the model easily on the screen. Then we're going to slice it so that you can see the interior parts. Okay. Alrighty. There are a number of ways to view the model. You can choose preset views, which would be in the different planes, or isometric. And as you saw, we can slice it. You can take a screenshot, snapshot. And you can also choose what unit you display the model, which can be different from what it was in SolidWorks or your CAD package. Okay, next we're going to assign attributes to the different parts of the model. And this GUI does that. Basically, we've got our different part names, which you saw before, and we're going to assign voltages to them. You can also assign charges, and if you're using that kind of problem. If you're going to be doing any of the thermal analysis that Took mentioned, then you would need to assign materials to the parts. We don't need to do that for just the electrostatic analysis and the beam. All we need to do is define parts having voltage, and then the code assumes they're conductors. And we've assigned the anode a voltage, and then finish the process. All of our collector, anode, and drift tube are ground, and the cathode is at minus 10,000 volts. The next step is to define those elements necessary for the beam optics. And there are different forms of emitters that you can define. Thermionic, a field emission. You can take a beam from either another ball run or a number of other programs and inject it. We're going to use a thermionic emitter. And this just shows selecting the surface of the emitter. And then that brings up this GUI. And to define that emitter, you can define, first off, you define the number of particles. And we're going to use 500. We're just going to leave it at one particle for a launch phase if you wanted higher resolution, or you wanted to look at thermal energies, spread of thermal energies, or momenta. You can define that. We're doing the emitter temperature at 1050 C, a typical one, and defining the material as tungsten. Oops, we lost it. Let's come back here. Okay. Yeah, it's going to go through. Sorry about that. Define it as tungsten, which gives us the emitter function. There's a little library built into this. And that will give you the emission density. Can do it space charge limit and temperature limit, which we're both doing both. You define, if you have a grid, you can indicate that. We don't. And define the anode cathode spacing. And that's it. Okay. Next, we're going to look at, sorry, before I forget, you can also define optically transparent parts, which is handy if you, for example, want to include a simple grid, which is you just want to see the effect of a grid, but you want to go through the effort of modeling, either creating it or actually doing the simulation of a mesh grid, a wire grid. You can just make a simple thin plate and define it as optically transparent. Then the electrons will see that as a fixed potential, but we'll go right through it. Okay. Then next we're going to look at the magnetic fields and electric fields. You can define other electric fields other than what the model will generate. But more often, what we want to do is define a magnetic field. And you can see here the various forms that you can use to create a magnetic field. Uniform magnetic field density. BOA has an integrated magnetosolver, which you can use for these simple types of solenoids and other field-producing coils. You can bring it in through Maxwell 3D or 2D. Pandira, if you have an axisymmetric problem, you can use it on 1D axial imported flux density. And then you can also bring it in from Opera. We're going to use a uniform magnetic field density, and this shows how you simply define it. We're going to use 300 Gauss. You can plot the field. In this case, there's nothing interesting to plot, but if you brought something in, you can plot it using a couple of different formats. Okay, next is the meshing. First, we'll define the mesh parameters. BOA can do a pretty good job in defining the mesh itself, but we also give you a number of different methods for defining the mesh, to refine it, as you will see, to make it particularly small mesh around small parts of the beam, stuff like that. In this case, we are going to let BOA do its thing. This will produce a fairly coarse mesh for a quick solution, and we'll look at refining that later. Okay, and as you see, it only took 0.76 seconds to generate the mesh. Okay, next we go to execute, and this is the GUI for that. As I mentioned, BOA has a way of refining the mesh, and that comes in this additivity. Right now, we're going to leave the number of additivity passes at 0, so it's just going to take the mesh that was defined before. And then the maximum number of iterations is obvious, and we are not, the beam that we have is non-relativistic low current, so self-magnetic field plays essentially no role. That's about it there, except that BOA does do parallel processing, and it will use up to the maximum number available on the machine. What I have found, though, in most of the problems is that the overhead to share the load across a lot of different threads is great enough such that it can actually slow the calculation down. And I limit it to about 4 threads. But this will depend on the size of the problem. Okay, so we're now going to execute it. And this is just running through it. On the lower right here, you can see a plot of showing what's going on. And what we're seeing is the error in the electrostatic and current, and then the actual current itself. And as you can see, the current is rising and gets up to a plateau. And that the BOA works like many other codes like this. It starts off with a small current, injects the beam into the electrostatically calculated fields, then takes the space charge of the beam, corrects the fields, re-injects, and keeps going until the answer doesn't change. And you can see here, this particular one took just under 32 seconds. So, and that's, as we'll see, it's a fairly crude solution, but it's really nice to be able to get something quick, to be able to see what's going on, at least initially when you're looking at a problem. Okay. Oops. We don't want that. Let's see. There we go. Okay. So now we can review the results. We're going to look at the beam optics first. And this shows the trajectories. The colors are signify the current in each trajectory. You can look at it as a sideways view of the trajectory. You can also look at it as a cross section of the beam, which is here. And then you can look at that in more detail. And you can see here that the beam is rotated. This is a feature, call it, of sheet beams. It's an E-cross B drift, and typically something one has to work around or try to mitigate. But you see it is clearly, you can see the outline of the beam. And again, this is quite a rough approximation. On the right here, you can see the lower right corner, the information about the beam, current, the power, but very importantly, the emittance and brightness. And then it gives some information about the geometry. That's largely relevant for round beams. But the emittance is a very important factor. Okay. And finally, you can display the beam on a surface. In this case, I put it on the collector, which is there. Okay. Now we've gone back and looked at the electrostatics, and this shows the potentials here. Let's put on some clipping there so it looks a little better. It's just rough, but again, you get a pretty good idea of what the potential distribution, field distribution is in the device. Okay, so to increase the resolution, we can do a number of things. One, we start with the emitter and simply just give it more particles. This will automatically increase the mesh density. And of course, just give you more particles for better statistics. And the other is in the mesh parameters. In this particular case, what I've done is set the mesh size in the system. And you can do this either as a fraction of the of the whole model, or absolute. I've chosen this, and I specified it at 2 millimeters. I've also specified a higher mesh on the collector, which is that face. And to do that, you simply select the surface and define the mesh size. And generating that new mesh, we now see we have a nice regular mesh. That's setting the mesh, and then a fine mesh here. And we've also got a fine mesh at the emitter. Okay, so again, we execute it, not using adaptivity. I'll show you that in a moment. Otherwise, it's all the same. And in this case, I won't bring you through the running of it. This just shows the output log, and it converged after 13 iterations and took just about 10 minutes. This shows the results. Now we have more particles, nice, even. And again, we get our our beam. Now, of course, it looks a lot more regular. Same kind of information over here. It shows the beam on the scatter plot on the collector. And now we can see, clicking on the power, we can see the power density, and it's in watts per meter squared, plotted there. And you can do a number of things, plot contours and stuff like that. But this, if you're designing a tube, very often you want to know what the power density is there. So, okay, and this shows the final mesh that it used. So, the fact that it took only 10 minutes seems to me pretty good. Okay, finally, this is the electrostatic solution. Now you see the potentials plotted here are nice and uniform, consistent with the higher density mesh. All right, I'm now going to turn to a generic X-ray tube, just to show you a little more of the modeling capability. Here's the geometry. The important features of this are, one, the filament emitter, and the anode, the target over here, on an angle, which is often the case in such tubes. This shows the a little more detail of that emitter, and it just shows the complex geometry that needs to be modeled here. What we would do for this is we would define all the surfaces on the helix to be emitters. Unfortunately, or depending on what flexibility you're looking for, SolidWorks made these up of a whole bunch of different surfaces. So we went through and defined each one. A little cumbersome, but not too bad. But other than that, fairly straightforward. There is no magnetic field here. And so now we go to the mesh parameters. In this case, we are since we care about the power density on the anode, the collector, we have defined a local mesh on that surface. We also set the mesh size. Okay, now we're going to use additivity. And we're not only on the electrostatic solution, but also on in the beam region. So now it's going to first look at the electrostatic solution and add the mesh where the energy density is highest, where we have in sharp features. And then it will also look where the beam is and add that. Okay. And choosing that, I limited this to 20 iterations just to save time. But as you can see, then when we get into real problems, it starts to take a bit longer. This took a little over 1,000 seconds. And here's the result. The beam goes primarily forward, but there was a little basically reflected and goes back. This is a very small fraction of the current. And as you can see, this particular one, the focal point was actually in front of the anode. Okay. So turning now to looking at a high resolution with a tightly focused beam. In this case, we're looking at a very simple gun consisting of a focus electrode, a cathode, the red part here, a vano electrode, and an anode. We don't have a target in this particular problem. This just shows a close-up of the cathode and the diode region. Okay, first I show you first the result because what we have here is a beam that starts out quite large and then comes to a small focal point. This is typical in X-ray tubes. And if you had to mesh this whole problem so that you had at least 4 or 5, and preferably maybe 10, meshes across the beam at its smallest point, then you would have a huge problem. It would use up a large amount of memory and take a very long time. Fortunately, BOA allows us to define the mesh locally and to get the resolution where we need it, and to use a large mesh where we don't. And this shows the mesh that we created. I'll show you in a moment how we did it. And as you see, it's a fairly rough mesh out here, just enough to define the cathode nicely. And then we have one mesh region, another one here, and another one, and I think there's even one final one right at the focus. So we're getting down to very, very small mesh and good resolution. And this just shows the beam that we're trying to do. Again, here's our mesh overlaid on that. Okay, and the way we did this is actually quite simple. What we did is define a bunch of so-called free regions. In this case, it's using cylinders because it's axisymmetric beam. And I started off with, there's one with the diode, and then went through successively smaller mesh size, ending up at a 2 micron size mesh, quite small. Okay, shows our problem. This is the, we're not using additivity because we've really extremely defined the problem with ourselves, and the rest is all normal. All right, and this problem took a while, and took 7,000 seconds. So definitely time for lunch while running it. Okay, we'll look at the beam optics again. And you saw those before. It's just a 3D rendering of it. Oh, very important. what I forgot to point out is that we use the symmetry. Since there are no magnetic fields here, we can use symmetry, and we took a quarter of the problem. This saves a lot of time, doesn't reduce the accuracy at all. The code keeps in track of particles that go out through a symmetry plane, and then it re-injects them appropriately so you don't lose any particles. It's a very accurate solution and saves a lot on time. Let's see. Okay, so that's it. And thanks a lot for watching. Some of the things I did not have time to show, but as Took alluded, BOA can do. It can, just by simply selecting a surface that the electrons will hit and stating that it's a secondary emitter, it will do secondary electron generation and tracking. It will go through multiple generations as you specify. Thermal modeling, which is a whole other thing. And you saw how we can show the power density on a surface. It will also, through a Monte Carlo routine, calculate the electron power deposition inside a collector. And then finally, calculation of magnetic fields. So thanks a lot. If you have questions, just let us know. Karen, back to you.
Great, thanks so much. Lawrence, did you want to talk a little bit about the pricing for BOA?
Yeah, sure. The current price for BOA is $12,000, which includes 1 year of support and maintenance. The renewal cost for the support and maintenance is $6,000 a year. And we also offer a discount for educational institutions. The code can be downloaded from our website, calcreek.com, and we will provide a free license for up to 30 days so you can try the code and make sure it meets your needs. So feel free to contact us at any time if there are questions or you would like more information. Back to you, Karen.
Great, thanks so much. So we've had a few questions come through. The first one here is, how does information from electron beam analysis get transferred to the mechanical analysis part of the code?
You don't mute, Took.
I can answer that question. Let me unmute myself.
Mhm.
The question is how to go from beam optics information into the trace analysis. That is the question. The two steps actually. First, we got to go from beam optics into thermal information. That means you do the heat transfer analysis to get the temperature profile. From the temperature profile, it's saved into a field, and it can actually import it seamlessly internally into analysis for thermal traces. So currently, one project, one can have a multiple simulation, one for beam simulation, one, and then we can go to heat transfer. After heat transfer, they can go into trace analysis.
Fantastic.
Did you
Thank
answer
you.
the question?
Yeah, thank you for that great explanation. The next question I have here is from someone who says, if I understand correctly, one can generate the model in a solid modeling program, and the geometry can be transferred into BOA. How does that work?
Mike, you want to answer the question?
Yeah, sure. Yeah, quite simply. I mean, you simply generate an ACES file from your solid modeler. Almost any solid modeler will do that, and just import the ACES file as I showed into BOA.
I would like to emphasize one more thing. Some users in X-ray community have a lot of fine features. They found that the parasolid model is actually more robust than ACES. In BOA, there are two options for the ACES model, for CAD model, either ACES or parasolid. The SAP is the ACES model. So both are available, can be imported into BOA.
Fantastic. The next question here is, are the material properties required for various analysis, magnetic, mechanical, included in BOA?
Uh, I can answer the question. There are a lot of built-in material, all for magnetostatics, electrostatic, also for heat transfer, also for stress analysis. And the one thing about the multi-physics tools like BOA, let's say you have a case of multi-simulation, multi-type of simulation. Let's say you start from beam optic and you're too lazy to assign any probability because the electrodes act like a vacuum, so you just ignore it, just like night read always do. You just set vacuum everything. So when you go to heat transfer, you say, oh, vacuum, don't like that. So you have to assign material to certain part. Now, the key point is when you do that, automatically it will update the material of the other simulation, the electrostatic simulation. And also the same thing when you go from heat transfer to stress analysis, and you decide to, I don't want to use moly, I want to use nickel, it will automatically update the material property in heat transfer and also in the electrostatic in the beam simulation. But now, because the material change in heat transfer, the simulation in stress analysis will complain, say, oh, you have to go back to heat transfer, redo it. If you don't want it, okay, we keep doing what you assume now, but it's not will not be consistent. So that is the error checking of the multi-physics tool in BOA.
That seems like a really helpful feature. Thank you, Took. The
Okay.
next question we have is, how can one tell if the mesh density is sufficient to achieve the desired accuracy?
Well,
That's a good
that's the
question.
art of the that's the art. Actually, there's still a little bit of the designer left in the process, and
Yes.
the simple answer is, which is standard, is that you increase the mesh density until the answer doesn't change.
Yeah, that's a standard answer. You actually refine the mesh one more time and see the result change or not. If not change, you're okay. But that's why adaptivity become into the play. It helps. But at the same time, it slows down the simulation. So that's a lazy way to do analysis by adaptivity. Just let it do all the work and you go get the data and come back and it's done. But it might
But you
not be
still have
good
to
either
check.
if you don't do it right, especially for beam simulation.
Yeah, you still have to check it. I mean,
Yeah.
even if it
Oh,
goes,
yes.
it's adaptive. It just adapts as many times as you told it to, and
Yeah.
so yeah, there's still it doesn't put the code doesn't put the designer out of a job.
That's why
Yeah,
you
it
need
sounds
my
like
kid.
you require the human element. There's still the necessary human element to make that decision. Fantastic. One more question here. If convergence is not achieved, can one restart the code to run more iterations?
Yes.
Mike, why do you answer that? You can answer
Yeah.
that, Mike.
Yeah. You just
Yeah.
there was a you may have noticed if the sharp eyes would have noticed that there's actually a little box to check that says restart from previous simulation. And yeah.
As
Awesome.
many
That
times
sounds
as you
wonderful.
want.
One more question just came in. Can one get technical support when evaluating the code before purchasing?
Lawrence, you want
Yes.
to answer the question? I can. I do normally, but I ask Lawrence first. Lawrence, you mute.
Yeah, absolutely. We want to be sure that you know how to use the code and that you're using it properly to make sure that your evaluation is going well. So we will help you set up a problem and walk you through all the various steps to do the analysis and the post processing.
Fantastic. Well, we're just about at time now. Thank you so much for participating. Thank you so much for our presenters. And if you have any questions, let us know. Thank you so much, and we'll see you next time. Bye.